Good morning, good afternoon, good evening, wherever you are on this planet, and welcome to our SETI Live. I'm Franck Marchis, senior astronomer at the SETI Institute, and today we are going to talk about a groundbreaking result which has just been announced by the Event Horizon Telescope Collaboration, or in short, EHT. And for this, we invited our black hole expert, astrophysicist at Stanford University, Dan Wilkins. Hi, Dan, how are you?
Hi, Frank. It's great to be here with you.
Where are you located right now, Dan?
I am currently visiting London in the UK.
Okay, so you back to the home country?
Yep, that's right.
Okay.
Back home for a few weeks.
Good. So today this is a kind of a special SETI Live because we are basically going to react on the announcement. So let's just say EHT and ESO announced and revealed the first picture of the black hole in the center of our galaxy that we are going to call the Milky Way black hole, or Sagittarius A-star with different name. But tell us, Dan, what exactly was announced, and what do you think about this discovery?
So the big headline today is that we've got the first image from the Event Horizon Telescope of the black hole in the center of our own galaxy. We've known that there should be a supermassive black hole in the center of our galaxy for a long time, and we've made a lot of measurements of the center of our galaxy that are sort of indirect evidence for there being a black hole. But now, for the first time, we're actually able to see the shadow, the black hole itself in the heart of our galaxy, which is really quite exciting to be able to see it firsthand.
So do you have the picture?
I do. I can bring that up now.
While you bring this up, I just want to mention to our viewers, you can tell us where you're watching us from. And we are going to take some questions from you in the next 10 minutes. Okay, so that's the picture. All right. Cool. It's a donut, right?
Exactly right, yeah. And pretty much the size of a donut. The image of the supermassive black hole in the center of our galaxy on the sky is the equivalent size to the size a donut would appear if it was on the surface of the moon.
Okay, so the central part, the dark part of the donut, it's basically the shadow of the black hole, which is the light. The light is we don't see anything here because the black hole is black by definition, and the bright features around, those are what we call an accretion disk or something like that.
Kind of like an accretion disk, yes. It's sort of a ring or a donut, if you like, of hot gas that's around the black hole. It's in orbit around the black hole, slowly falling into the black hole. So we're seeing the light from that hot gas around the black hole, and then that shadow in the middle where the event horizon of that black hole is. So no light can escape from the black hole. So that center of the image looks dark.
Okay. Just to clarify, are you involved in this research yourself?
I'm not. I am an enthusiastic onlooker to the Event Horizon Telescope team. So I work on other aspects of black hole research. So I'm a huge fan, and obviously I keep a close eye on the developments from the EHT for my own research. But yeah,
okay. So that's
just an onlooker.
So that means you can speak freely and tell us what you really think about this result.
Yeah.
So before you do that, I would like to mention that we have people watching us today from Scotland, not too far away from you, Spain, Louisiana, Colorado, Oak Ridge, Tennessee, Leonora in Washington, New York, Philippines, Gothenburg in Maryland, Germany, Italy, Connecticut, Atlanta, Georgia, Berlin, Germany, and Weymouth. Sorry for the pronunciation of this one. If someone can tell me where is Weymouth, that would be very useful. It may be UK, but let's see. So ESO and EHT announced this as a kind of a groundbreaking result. Can you explain to us why this is an important moment in the history of astrophysics?
So I think the real importance of this image is that for the first time we're actually seeing what is in the center of our own galaxy. The EHT a couple of years ago in 2019 produced the first spectacular black hole image. That was the black hole in another galaxy, a galaxy called M87. And that black hole really is somewhat different to our black hole. It's feeding on material and it's shooting out a jet of plasma close to the speed of light. It's what we call an active galaxy or an active galactic nucleus. Whereas our black hole is much quieter. It's a much calmer system in the center of our own galaxy. So we're now seeing, essentially for the first time, really, the image of a quiet black hole in a galaxy such as our own. And just being able to see the black hole in our own galaxy, I think is an important achievement in and of itself.
Yeah. Probably our viewers probably remember M87. In fact, you can stop sharing your screen. Then M87 picture kind of look like this one as well. But during the press conference, the scientists clarify that if our own black hole, Sagittarius A-star, was the size of a donut, the size of M87 black hole is basically the size of a football stadium in scale. So M87 is huge. It's a huge black hole. We have an idea of the mass of those bodies because we call them supermassive black hole. But both have supermassive black hole, but there seems to be difference in size and in mass, right? Do we have measurement of this?
We do, yes. So we can measure the mass of the black hole Sag A-star in our own galaxy, both from that Event Horizon Telescope image and also from the way the stars move around in the center of our galaxy. So in Sagittarius A-star, the black hole it's about 4 million times the mass of our sun.
Aye.
The one in M87 is almost 1 billion times.
It's a billion times. Right. So before we go into the details of the black hole, we have people joining us from Hood River, Oregon, Vancouver, Canada, Los Angeles, Glasgow, Turkey. And I just get the clarification that Weymouth is in the UK. And the reason I knew that is because as soon as there is a name of a city which a French person cannot pronounce, it's basically in the UK. I don't know why, but I think it's a master plan from the English people. Then we have Belgium, Illinois, Austin, Texas, Florida, on the Bayou of Louisiana, Poconos, Pennsylvania, Copenhagen, Denmark. We have people from everywhere, India, Santa Fe, Argentina, and Denmark. Apparently, everywhere in the world, people have heard about the news and everybody is interested in the story of black holes. So let's continue this conversation. So we have an image, okay? So you tell us basically, describe briefly how this image is about. So what can we learn from this image?
And there's a huge amount we can learn. And so at the most basic level of that image, we can look at the ring and we can look at the size of the ring and the size of the shadow in the middle. And that tells us a couple of different things. If we know how far away that black hole is, which we do for our own galaxy, we know how far it is to the center of our galaxy. The size of the ring in that image tells us, first of all, about the mass of the black hole. That's one of the ways we know how big the black hole is. Because the more massive a black hole, just the bigger its radius is. The radius of a black hole scales linearly. So if you double the mass of the black hole, it will have twice the radius. So we can see that. And the other thing we can actually test is Einstein's theory of gravity, general relativity, which is the theory that explains gravity as far as we understand it all through our universe, whether it's the gravity in our solar system, the gravity that holds the galaxy together, or the gravity of the universe at large. And by measuring the size of that image, measuring the size of that ring, we can actually see that, yes, the image of the black hole in the center of our galaxy does in fact agree very well with Einstein's theory of general relativity. This black hole looks exactly like a black hole should, if general relativity is correct. And this is really important because we can do lots of experiments around Earth and around the solar system, testing our theory of gravity in sort of fairly weak conditions, the gravity that holds us onto the Earth or the gravity that keeps us in orbit around the sun. But when we're able to look at a black hole, we're testing really the extremes of gravity. This is the strongest gravity that we know of just outside a black hole. And we can see that, yes, our theory of gravity that we have still works when we turn the gravity up as far as we think we can.
Oh, hey. So we are getting questions already. And there is one question which is related to that. So from this image, we also learn about the orientation of this black hole. That was mentioned in the press conference. Can you tell us a bit more about this?
Yeah, so we can learn about the orientation of the black hole by thinking about exactly what it is that we're looking at here. So what we have is the black hole itself, which we can think of this spherical region of space that light can't escape from. So there's sort of this dark sphere in space that anything that goes inside we'll never see again. But then around the black hole, we've got this hot gas that we're seeing in the ring. And that gas is in orbit. It's a sort of donut shape. So it's a ring of gas with a hole in the middle where the black hole sits. So by looking at the shape of that ring, we can work out the orientation of it with respect to the Earth. So you can imagine if you're looking at a ring face on, you'll see it as a circle. But then as we start looking at it edge on, it will become elliptical until we're looking at it completely side on, when we'll just see the band of gas instead of the ring. So we can see that we're looking at this. It looks like we're looking at almost face on because we're seeing the dark ring in the center. And then we can also learn about how that ring is moving based on the bright and the darker parts of the image.
All right. Something very surprising to me, two things. One, the two black holes we observe, both of them are almost face on.
Yeah.
Isn't it weird?
Yeah, I have to say that's one thing that really struck me. And there's a second thing here as well. So the picture that we have of our Milky Way galaxy is that our galaxy is a spiral galaxy. So it's a flat disk of stars. And we live on the edge of that spiral. So when we look to the center of the galaxy, we're looking through the ring of stars. So you've got this flat galaxy so that the ring of the galaxy is oriented this way. But we're looking at the black hole in the center, which you might think is oriented the same way.
That's also, yeah.
We're looking at it face on. So it looks like the black hole in the center isn't lined up with the rest of our galaxy. So I think it'll be interesting to.
This is a very interesting result and surprising to me too, frankly.
Yeah.
So they mentioned that they will in the future take more data, of course, and maybe we can discuss first that how we take the data, because that's something we did not discuss. So this is not an image you take with a telescope. You don't take this small telescope or any big telescope and point towards Sagittarius A-star and see the black hole. Why is that possible?
So when we want to look for things that are really small in the sky, we're looking for things that appear really small. What we need to do that is what we as astronomers call angular resolution. So that's if there are 2 points of light on the sky, so 2 stars. Our angular resolution is our ability, if those 2 points of light or those 2 stars are very close together, our resolution is how well we can separate the images of those 2 stars. If we've got high resolution, we see them as 2 points, but as the resolution gets lower, they'll blur together and we'll just see a single point.
So
and the way...
Go ahead.
I was just going to say the way to get... the fundamental resolution you can achieve with a telescope depends how big a telescope is, the diameter of the telescope. And here we're talking about something that's the equivalent size on the sky to picking out a donut that someone's left on the surface of the moon. So we're looking at something that's an incredibly small image on the sky. To resolve an image that's that small, and a telescope like you've got behind you is nowhere near big enough to do that. You need a telescope that's about the size of the planet Earth to be able to see the actual event horizon of the black hole in the center of our galaxy.
So that's the reason they use this EHT or ETH, depending which language you're speaking. And it's basically an array of antennas distributed across Earth. And what they explain is that they observe by pairs. So they use an antenna in Europe and an antenna in Chile, for instance. They observe the black hole at 1 to 3 millimeter wavelength. And they do the same at different combination of antennas. They are almost on every continent now. And they combine these data. The combination of the data, it's something that I liked in the press conference. They described it. It's not easy, okay? Because they have to basically record terabytes and terabytes of data. I think they said 6,000 terabytes of data to just create this image. And they have to calculate the combination basically of this antenna. And there is multiple solutions, unfortunately, of this combination, because one of the reasons is that our black hole spin on itself quickly. And this make that during two pair of observation, there is some changes during the observation. So it's like one of the scientists say is like trying to take a picture of your kids running in the dark, in the night. It's very difficult. You have to have an extremely sensitive instrument to be able to get this, to be able to take these observations. And that's why it took so long to do this. Because I mean, the EHT project started 30 years ago, if I remember. I do remember, in fact, when they announced these attempts to put together this large array. So 30 years later, we finally have an observation of the black hole in our galaxy. That's the amount of time it took to this observer to hammer all the tiny details to be able to get this observation, to be able to analyze this observation. They have to take advantage of the progress of computer as well over the 30 years to be able to do those calculations. So we have now a picture of a black hole. We know it's different to MMT7. So what is the next step?
I think the next big step is actually there's another aspect of the Event Horizon Telescope data that we haven't heard a lot about so far. And this is something called the polarization of the light. So the simplest way to think about this is that we can think about light as a wave traveling through space. So as the light travels across space, it's a wave that we can think of as going up and down. Now, the polarization of the light is actually which direction the wave is oscillating in. So you could have a wave going up and down as it travels, or you could have a wave oscillating in the horizontal plane. And the telescopes that form part of the EHT network are sensitive to the polarization of the radio waves that they're detecting. They can measure that. Mm-hmm. And the polarization is really sensitive to the gas around the black hole and the magnetic field that's around the black hole that's interacting with that gas we're seeing, that's heating that gas we're seeing. So the really exciting, I think, next step for both the Sagittarius A-star and the M87 images, in fact, they've already released some of the polarization for M87, is actually being able to learn more about exactly what is happening to that hot gas around the black hole. What is happening to that gas as it falls into the black hole? What is the black hole doing to it? And how is that gas getting heated up to produce that ring of light that we're seeing in the image? And this is going to tell us really quite fundamental things about how black holes feed and how the black holes in the center of galaxies actually grow to become supermassive black holes.
Excellent. That's a very good transition for the questions we're getting from people here. Thank you, Dan, for this explanation. So how often black hole swallow stars like the black hole of our own galaxy? Do we have an idea of the growth of those black holes? Can we quantify this now?
Yeah, so in terms of swallowing stars, we don't think that that's really how the black holes gained most of their size. So we think in a galaxy like our own, the black hole will only actually eat one entire star every about 10,000 years or so. We've seen this happen a few times. We've actually got lots of observations now of black holes swallowing stars. It's something we call a tidal disruption event, because the tides around the black hole rip the star apart as it comes in, and it produces a fantastic firework display for us. And we've seen a few of these. It's once every 10,000 years per galaxy, but luckily there's lots of galaxies. But I think it'll be a long time before our black hole eats a star.
Yeah, one scientist said that the black hole grows by hitting the equivalent of one rice every 1 grain of rice every million years. It's not.
Yes, yeah, that's
scary.
Our black hole is on a very strict diet. It's some of the black holes that actually I study as part of my own research are much more active. They're much greedier and will eat something like 100 Earths a year. But they're really quite different to the one in our galaxy.
I think it's fascinating that now we are starting kind of classifying black holes and seeing differences. Before it used to be, there is black hole in our galaxy, done. Now we're starting studying them to the point that you have split the community in those who study supermassive, extremely energetic black hole to those who study the black hole in our galaxy coming from the tiny one coming from the supernovae remnants. It's remarkable that we are this level now in the study of those exotic bodies.
Absolutely.
We have more questions. So one of them is, can you tell us, I like this question. I think you mentioned this during our SETI talk, but what's the relationship between those black holes and the formation of galaxies? Do we know?
So this is actually one of the biggest mysteries in modern astrophysics, and it's something we're hoping to answer with the next generation of space telescopes. So I'm not talking about JWST here. The JWST will do a little bit. I'm talking about the telescopes that we're planning beyond JWST. We know that every major galaxy, so the galaxies like the Milky Way or M87, at least all of the major galaxies have a supermassive black hole in the center. But we don't know how that black hole got into the center of the galaxy. We don't know if the black hole formed very early on and then the galaxy grew around it, or if the black hole formed in the center of the galaxy from sort of leftover material when the galaxy was growing. It's one of the big questions. And in fact, we see one of the amazing things we've observed is when we look at really distant galaxies. So these are galaxies that are so far away that the light has taken 10 billion years to get to us. So these are some of the first galaxies that formed in our universe. These early galaxies, when the universe was in its infancy, already have a really big supermassive black hole in the center of them. So it's a little bit of a puzzle as how that black hole grew so big so quickly. And I think that's a really exciting research topic to keep an eye on over the next couple of years or even couple of decades.
So very dumb question, but please answer to me quickly. How do we know that a galaxy with a redshift of 3 has already a black hole in it? How this is done?
So the easiest way with those distant galaxies is when that black hole is something called a quasar. If that black hole is feeding on a lot of gas, it lights up to be one of the brightest light sources that we see across the whole universe.
Good, thank you. So another question, can we say that there is a relationship between the galaxy size and mass and the black hole size and mass now? Or it's too early?
Yeah, absolutely. And this is actually one of the most important bits of evidence in our understanding of how galaxies form, is that the mass of the bulge of stars in the center of a galaxy is very closely related to the mass of the black hole in the galaxy. This means that the growing galaxy must know something about the black hole that's in the center. And one of the most amazing things I think about black holes is when we see these quasars and these other bright black holes that are feeding on gas, and this gas that's falling into the black hole produces enormous amounts of light. All of the energy that comes out of material falling into black holes is so great that the feeding black hole growing in the middle of a galaxy must have had a profound effect on the galaxy itself. So we know that the black hole in the center of a galaxy is a really important force in governing the growth of the galaxy, making sure the galaxy doesn't grow too big.
Yeah, that's a very important point. In fact, it seems to us we are far away from this black hole. We are like, what, 70,000 light years, something like this, roughly?
About 30,000.
30,000, yeah. So a third of the diameter of our galaxy. However, the forces we are talking about here in terms of energy, the amount of energy, for instance, emitted by those black holes when they have this, like the one of MMT7, is enormous, right? The amount of light and energy, for instance. So this should have an influence on the surrounding planetary systems. So in the inner part of our galaxy, the condition was extremely different, probably 10 billion years ago, when the galaxy had formed 14 billion years ago. So, I mean, we are the SETI Institute, so I have to mention that we care about the formation and the evolution of life. So the presence of a black hole in the center of a galaxy has probably an impact on the formation and the evolution of life in the inner part of the galaxy. It could be anything such as those civilizations over there that appear probably before us because the stars are older in the central part of the galaxy, was in an environment which was probably extremely chaotic in terms of energy. I can imagine like those jets may have sterilized the planets completely, the gamma or the X-ray emission as well. So maybe it's good we formed only 4.5 billion years ago as a planet and as a biosphere as well, and we are far away from the black hole, because probably that's allow us to have a more stable environment, something more appropriate for the formation and the evolution of life. Maybe I'm pushing it too far here, but I want to link a little bit this.
Yeah.
It's important that we understand that this research in black hole is not only about black hole per se. It's like the formation, the evolution of galaxies, and they are a very good proxy to truly understand this. Someone just asked exactly the question I just mentioned. So the evolution of Earth and etc. So I'm gonna skip this one. I'm gonna take a last question. Yes, is there any relationship between black hole and dark energy or dark matter?
I think that's an interesting and complicated question. That there's a lot of sort of really fundamental particle physics research going on at the moment. So as we think about black holes, we don't normally on a day-to-day basis think too much about the dark energy and the dark matter. We know that dark energy becomes important in pushing the universe apart and expanding the universe on the largest scales. But on the small scales around a black hole, we think that the strong gravitational pull towards the black hole is much stronger than the dark energy pushing out. So we don't think the dark energy is too important there. And likewise, the dark matter. If there is dark matter close to a black hole, the force of gravity should attract it to the black hole. It should get pulled into the black hole like any other matter that's around. It's just when we have a galaxy like our own, the the dark matter tends to be much more extended. So our galaxy is sort of this flat disk, but then we live in a dark matter halo that's much more extended around the galaxy, because the dark matter didn't collapse into the galaxy early on. So yeah, they certainly do interact with the black hole. They're just, as far as we understand at the moment, they're not too important in governing the behavior around the black hole.
Okay. Well, thank you very much, Dan. Before we leave, tell us a bit about your research. You're in London, but I'm assuming you're coming back to California soon?
Yeah, I'll be back in California in a couple of weeks, and yeah, so my research is about the black holes at the other end of the scale to Sagittarius A-star. A lot of what I'm working on at the moment are those black holes that are feeding on enormous amounts of gas. I mean, I'm really interested in exactly what happens to that gas in its final moments as it falls into a black hole, working out how we can use the light that hot gas around a black hole emits. We can use that light by looking at how it actually then reflects back off the gas falling into the black hole. So we're working on new ways of creating images and creating maps of black holes that are much more distant than the ones that we can see with the Event Horizon Telescope. So we hope our research will be complementary to the EHT in producing 3D maps and images of many more black holes that are further away, and then figuring out exactly what it is about a black hole that kind of paradoxically allows a black hole, something that swallows all light, to actually produce some of the brightest things that we see in the sky.
Okay, well, thank you. I hope to have you back soon in California and back on SETI Live or SETI Talk, hopefully in person. So
yes,
I don't
that
think
would be great.
it would be great to see each other. We're not that far away from each other. So thanks again, Dan, and to all our viewers. This was a SETI Live. We talk about Sgr A-star, the black hole in the center of our Milky Way. Next week, we have a SETI Talk. It's Wednesday, May 18 at 7 p.m. And the SETI Talk will be about the TESS mission and the search for ET, how we could find megastructures around stars observed by the TESS mission, and how we can find technosignatures and why it does matter. So if you want to hear about this, we invited two scientists, Anne-Marie Cody from the SETI Institute and the Noah Friends from Berkeley City, to talk about this project. And register, go on our website at seti.org and search for the SETI Talk. You will be able to register. If you want to know more about the SETI Institute, as usual, follow us on social media. We are on every platform, I think. Thank you, Bess, for taking care of that. I know it's a lot of work. We also have a website, seti.org. You can see the news about our research, our scientists, our education and outreach program. If you feel inclined, you can make a small donation. Just go at seti.org/donate and choose the right place to make a donation. So for instance, you can support this program by supporting the outreach program. Thanks again, Dan. We see you soon. Thank you to all our viewers on this planet, and enjoy this picture. That's not the last